Okay, we are live.
Right, we will be continuing our morning hearing on the importance of Old Forest, and we welcome Dr. Ali Kasiba. Welcome.
Thank you. Thanks for inviting me. Thanks. And I'm happy to be here. Yes, I'm Ali Kasiba. Alexandra Kasiba is my full name. I go by Ali. I'm an extension assistant professor at the University of Vermont, and in that role, I serve as a state extension forester. My background and expertise is that I'm a forest ecophysiologist. That means I am a tree physiologist, so I think about how trees work, how they respond to environmental conditions, and then how that impacts the greater forest ecosystem. I use that information to help folks, landowners, foresters, loggers, conservation commissions make informed decisions in their woods. Can I go forward? There we go. So just a little bit blurb about UVM Extension Forestry. It's actually new. I stepped into this role 2 years ago, and we had a 7-9-year hiatus in this position being at the university. All land grant universities have extension, and it usually focuses on agriculture, also forest management, helping people, farm workers. The 4-H program is part of extension. And so it was a great opportunity to join the UVM. I got my master's and PhD at the University of Vermont in the Rubenstein School of Environment and Natural Resources in forest science. And I've done a number of things since then, including I worked at Forest Parks and Recreation as the climate forester, and I was the first climate forester in the country, which is a pretty cool role to have. So now in my role as faculty at the university, I do both research and teaching. And my teaching is not in the traditional classroom. I teach out in the world. So I do lots of, this is an example of a in-person workshop I gave to sugar bush managers. So I'm talking about how climate change impacts sugar maple and things that they can do in their sugar bushes to help prepare them for those impacts. And I also do lots of field research to understand forests and make better decisions. So I was asked to come here to talk about why old forests are important. Some of the things I talk about are going to be redundant to what Liz talked about, but maybe a different aspect I'll touch on. So Liz talked about this already. Why old forests are important is that they are uncommon in our area. And this is actual data from New England and New York from the Forest Service. So there are permanent plots around the country, actually, that are forest inventory and analysis plots. They're measured on a rotating basis. Here in Vermont, they're measured every 7 years. So a subset of plots are measured every year, but one individual plot is not remeasured until 7 years. And so it gives us a snapshot on what species are growing, what mortality rates look like, also gives us a snapshot on land use change. And this is showing approximate ages of those plots. In the dark blue is Vermont, but generally you see this pattern, it's similar across the states, is that the majority of our forest age is between this narrow band of 40 and 100 years old. And this reflects, as Liz talked about, this land use history. In Vermont by 1900, we had our lowest forest cover, it was about 30%. And it is a remarkable story of the recovery of our forests. When farmland was abandoned, forest is our natural vegetation cover in most of our areas in our state. So trees just naturally regrew. And now we have about 75% of our state is covered in forest. And it's pretty remarkable, the species diversity that naturally occurred and you know, as that came up in these old fields. I'm going to provide, you know, Liz talked about some of definitions, similar how I describe old growth forests, and I'll kind of break apart how we can think about different ages. So old growth forests, never cleared for agriculture, minimal human disturbances or large natural disturbances. We generally, you know, use this, we use a proxy of tree age as time since disturbance. So generally we're looking for trees that are at least 150 years old. That sort of gets us to that pre-European land clearing time. That continuity of process is happening. So natural processes are happening, trees are dying, new trees are growing. There's a lot of complexity that takes time to happen. And that's a really small percentage of Vermont's forests and the region's forests. Then we have this other class of forests, secondary forests. Liz talked about this. These were ones that were, really fully cleared for agriculture, or were harvested for timber very thoroughly, right? So clear cuts or something that really removed all of the growing stock. And then those subsequently regrew. And so you see the difference between those two types of forests. That top photo is an old growth hemlock forest. You see there's different tree ages. There's lots of down wood on the ground. That bottom photo is a very typical second growth forest in our state. We call it old field white pine. Farmland was abandoned. White pine often grew up on those stands. All those trees are the same age. They're growing very close together. They're the same size. There's not a lot of structure or diversity in that forest. But we do have this middle group of forests, and this is where we can find some old forests, and I'll talk about this. This is this group that never fully cleared for agriculture, but they did have some level of human disturbance. Maybe they were selectively harvested. Often we had woods around here that were used as night pasture for cattle. So cattle were put in those woods at night as protection from weather events, or they're just disturbance-prone sites. So they get a lot of windstorms, other events that come there, and the trees never really get that old. And so this is where we can find some old forests, because we can find places where there are trees that are over 150 years old, and they might have some characteristics that we see in old growth forests. This bottom group, the secondary forest, there might be trees getting to the point that they're 100, 150 years old, depending on when they were abandoned and regrew, but they really have not had time to develop those characteristics that we see in old forests and old growth forests. Because that really does take time for trees to die, other trees to occupy that space and that complexity to develop. So this came up in Liz's presentation, this question of how much old growth forest would we have had, or how much forests of different age classes would we have had in the past? The issue with this is we don't actually know how frequently disturbances affect an individual forest, and that really dictates how old the trees can get. And so it depends on the return interval of natural disturbances. And this is great research by Lorimer and White back in 2003, and they looked at different types of forests and the potential age classes of those historical forests based on different disturbances. So here I'm showing northern hardwood forests, and they show in this light blue, if you had fire that happened every 1,000 years and windstorms that happened every 1,000 years, you'd get the age class distribution represented in the light blue. If you had longer disturbance intervals, so that means an individual stand might only experience fire every 3,000 years and wind every 2,500 years, you get the dark blue. And so you can see that the distribution of age classes really varies. With that longer return interval, you could have a lot more of the landscape in that 300-year age class than in that shorter return interval. So this is one of these unknowns. We don't have records that go 1,000 years, and so we use proxies to try to disentangle these, but we don't really know. And this is an example for a spruce northern hardwood forest where we know disturbances were different. Different types of disturbances affect different forests, and there's different return intervals, as you can see, and this is showing 4 different types of rotations, but basically that same pattern is that it dictates that age class distribution. So if we're looking at stands over 150 years old, over 300 years old, it depends on how frequently they experience disturbance. Is there a question?
Well, just it's also as a scale, what area are we measuring for the disturbances, right?
Right. So this is at the stand level. If a stand experiences disturbance in that frequency, the trees they'll die before they can reach a certain age. And that's how we get different age classes across the landscape. So how are you
defining stand?
An area of forest. Yeah, can vary based on, yeah. Another important factor of old forests is they have big trees, and Liz touched on this. And one important component of big trees is that they disproportionately store a lot of carbon that was removed from the atmosphere. And so this is showing a schematic for sugar maple. Basically, this idea is that as a tree grows larger in size, it has an exponential amount of carbon that it stores. And that's because trees are three-dimensional objects every time they grow, and they really do have to put on new wood every year. This is how they survive. They're putting new wood, which is made of carbon, on every surface. So on every branch across the whole stem, they have to put more wood. And so as they grow larger, they store more and more carbon. So we do know that large trees are really important in carbon storage. And this is showing some data from old forests and old growth forests across the region. It's only from 20 sites. We just don't have a lot of old growth and old growth forests, but this is showing carbon storage, which is in the live trees. So carbon storage is the amount of carbon you have in the forest right now. It's the amount of carbon that I use the analogy, it's like your bank account. Amount of money you have today in your bank account is your carbon storage. And you can see in that figure, as those forest stand ages get bigger, you have more carbon stored in that forest. And we see that as a pretty general pattern. If we had the individual plots on here where we got that data, there would be variability. Some plots would be above that line and some would be below that line. But when we take sort of the average, we get that pattern. Yeah.
Representative Bartholomew.
On the graph, the slide 4
Yeah.
with the tree, large tree. I'm just wondering, as that tree gets bigger, it means that there are other trees that aren't growing around it. So how does
Absolutely.
that play in with that? Where you
Yeah.
have fewer trees, but one. What does
Great.
that do to the
Yeah,
graph?
so you'll see here we have this exponential line, right? So that continues to grow up. This is carbon storage in an individual tree. When we look at carbon storage by acre, so this is usually how we measure forests, you'll see that it's a little bit of a different, we have this sort of tapering off of the carbon storage. That is because when you have forests that get older, right, you have trees grow bigger, some trees are going to die. Not every seedling and sapling that establishes in a forest is going to be able to compete. And some just die out because of resource limitations. And so as we have these forests that become, go from 100 to 200 years old, there's going to be bigger trees, but there'll often be fewer big trees. Some trees die, you get more complexity in that forest. And so you have fewer trees per acre in many cases. And so when we look at the rate of sequestration, so sequestration is the rate that trees absorb carbon dioxide from the atmosphere. This gets talked about a lot because this is the way we down draw carbon dioxide from the atmosphere is trees take it in and then they store it. And that's the figure on the right. We call it flux. Negative numbers are good. That means more absorption of carbon dioxide from the atmosphere. So bigger negative numbers are more sequestration. You can see the pattern of younger forests absorb carbon dioxide, sequester carbon dioxide at a higher rate than older forests. And that's just a phenomenon we know about. And because those older forests, they have more dying trees. They have logs and dead wood that are decomposing, and decomposing wood emits carbon dioxide back to the atmosphere. And so we have this pattern of older forests store more carbon, but they sequester carbon at a slower rate.
Representative Miller.
Do you have the graph that goes all the way back to zero? When you're starting at like 120 years there and going
Yeah.
from there, what does it look like all the way down to the youngest?
Yeah, I didn't include that here because these are data actually from Bill Keaton's work looking at old forests and old growth forests, but I do have those data. And basically, if you start at nothing in an old field, you're going to get an increase in carbon. The peak of sequestration, it depends on the forest type and location. It's anywhere between 20 and 60 years old is usually like the most sequestration we get, but it can vary. Yep.
Representative Pritchard.
Is the ability to absorb based on mass? And so I guess what I'm saying is that the big tree, if there's amount of small trees that equal that mass, is it equal sequestration, or is it because it's a bigger tree, it's able to do more, or is it based on mass?
It's actually usually based on the amount of leaf area, so the amount of the canopy size, but we have to be careful about talking about a tree versus a forest. So if we just look at trees, if we have a small tree versus a big tree, that big tree is actually going to sequester carbon pretty fast. So that's what this is showing, this graph, right? Because it has a lot of leaves, it has big leaf area, it's photosynthesizing a lot. But when we get into the forest, we have a lot of other things going on, including decomposition and respiration. Respiration is a natural process of every living organism releases carbon dioxide back out to the atmosphere, including living trees. They use their own stored sugars from photosynthesis, and they use that for their metabolism and growth. So they are actually, we think about trees as always taking in carbon dioxide and releasing oxygen. They also do the opposite of that when they're metabolizing. And then all the other living organisms in the forest, from insects to fungi to bacteria, are also releasing carbon dioxide. So we get into a forest, it gets incredibly complex in that you have carbon dioxide coming in through photosynthesis, but you also have carbon dioxide leaving through all these processes, breaking apart of dead wood and leaf matter that organisms are eating, and then they're also respiring out. And then, of course, when we have forest fires, we also emit carbon dioxide through that combustion. So that's another way that can happen.
So it's part of what it also creates.
Exactly. Yeah. So this is showing it for a forest. So that gets much more complex when we talk about a forest. So when you think about an acre of forest, and that's why it is very careful to show it by an area basis, in an acre of forest, you might have fewer large, as the forest ages, you get fewer large trees. You'll also have standing dead trees. You'll have trees on the ground. You have a lot more complexity. That does mean more emissions of carbon dioxide through those natural processes. When a stand is young, those trees are just trying to grow tall and outcompete each other. So you get a lot of sequestration and you don't have as much emissions at that point. And I will say, I have, if you're really, I can come do my road show is talking about carbon, talking about climate change impacts. And so I did write this guide to forest carbon in the Northeast. It comes from, I did a series of articles in Northern Woodlands magazine on carbon, and we then published them in this guide. So they're meant to be for a very general audience, but they get into a lot of the details about how carbon moves through a forest, ways we can think about enhancing carbon benefits. And I also talk about carbon offsets and what those are, how landowners should navigate those. And I'm happy to.
I believe you all brought copies of that.
Yeah, I have a bunch of, and I did.
Yeah, I bet we'll all want them, but you can wait.
Yeah.
Let's wait till.
And I did send it as an electronic copy too, and have it on my website. So this was showing just live trees. So that's just the living trees. This is the carbon that they store and sequester. But we also have these other pools in the forest. They're reservoirs that can absorb carbon, or they get carbon transferred from live trees, really. And then they also can release carbon dioxide, as I mentioned. But when we look at the carbon storage, again, this is forest age. This goes from 0 to 200. So this is showing a little bit of that younger age class. We have live trees in sort of that, light green color. And then we also have soil in that top line. You can see that soil in those oldest age classes is storing more carbon than in middle-aged class forests. We also have the forest floor layer. That's sort of where our leaf litter is. That stores quite a bit of carbon. And then we also have two components of dead wood at the bottom. So that top orange line are logs on the ground, and the bottom light orange line are standing dead trees. And so this general pattern, you can see there's variability based on exact forest age, but this general pattern, we see a lot of carbon stored in our old forests.
Is this data from the Northeast?
This data is from, again, those forest inventory and analysis plots I mentioned. It's from the Northeast to the Midwest, which we call like Region 9. If you're familiar with the Forest Service, they looked at that sort of. So it's all similar forest types, but it does go further than, our region specifically. Yeah. The challenge really is the number of data points we have to do some of this analysis. And so Liz talked about this quite a bit, this idea of structural complexity. And so we do know that the amount of stored carbon we see in old forests is really related to this concept of complexity as well as diversity. So complexity is this both horizontal and vertical distribution of layers in the forest. And that seems really technical, but basically it's this idea that we have trees of many sizes, ages, conditions. We have shrubs, herbaceous plants on the forest floor, standing dead trees, downed logs, and also irregular gaps in the canopy so that we don't have a lot of uniformity in our forest. There's different conditions from here, there, different layers in the forest. And we see in a number of research studies that when we have more complexity, so this top image is showing carbon above ground in two different forest types. The first one is sort of hardwood stand with low structural complexity. And we see that when we have higher structural complexity, there's more carbon. This lower left figure is from old growth forests in the Adirondacks, where we do have quite a good component of old growth forests and old forests, and showing over those stand ages that we get more biomass, which is really a measure of carbon in above ground, in live trees and as well as dead trees. And there's also been analyses to look at this kind of idea of complexity as putting it into an indice. So they use this H index, which is a measure of variability in tree size and height and number of species. You see that trend, we get more carbon as that H index increases. So there's just different ways scientists have tried to quantify the relationship of carbon and this idea of complexity and diversity. Another thing we see in older forests, right, this continuity of process is that we see this complex mosaic of conditions, right? Old forests have young trees. That's a really important component. And when we have these natural disturbance events, we get a range of tree sizes, we get dead and down trees, we get different canopy strata, and we get gaps. And this is research showing by estimated stand age, the gap size. And so you actually see in these older stands, we get these bigger gaps. Basically, this concept that those forests have been forests for longer periods of time. As a forest is there for longer periods of time, it is subject to more probability of disturbances. So one might just knock one tree down. Maybe a microburst comes in and knocks a 2-acre area of trees down, right? And so it's just about this probability of disturbance, that time that forest is there, and we see more complexity. We do have a lot of research that supports that forests with greater species diversity and structural complexity are more resilient to climate change. And this is a concept, that expands beyond forests, this idea that, when we have different types of things in the forest, different species of trees, different ages, they're not all susceptible to the same disturbances, right? We get an insect comes in, usually insects affect one species of tree and not others. Things like windstorms will maybe affect the overstory large trees and not the younger trees. So when we have diversity complexity, when a disturbance does hit that forest, it's able to bounce back, right? It's able to remain a forest. So, 2 examples. Again, this is a picture of that sort of old field white pine, classic Vermont forest. I see that forest is very vulnerable to a single disturbance. All those trees are the same size. They actually have very small. One thing I see as a forest ecologist, they have very small crowns. So there's not a lot of leaf area up there. That is a good indicator that those root systems are pretty small. These types of stands come down very easily in a windstorm. There's no small trees in the understory. So it'll take a while for that forest to then regenerate and have trees again. Versus the stand on the right, there's a lot of different species I see here. There's trees of different ages, different sizes. Event comes through there. That's likely going to remain a forest and be able to bounce back much quicker. And so we see some characteristics of healthy, resilient forests, multiple species presence, this idea of vertical and horizontal complexity, as I mentioned, successful regeneration, which is really being hampered by intense browsing by white-tailed deer across our state. We also want to see things like hydrology and other ecological processes well functioning. And we do see that those have been impacted in many of our second growth forests where there was maybe the land was plowed for agriculture. So that meant that the soil was actually physically disturbed, churned up. We see that as evidence of very flat forest floor, whereas normally a forest floor should be really undulating, be very complex. So that affects hydrology. We do in some cases have legacy roads that maybe were put in a long time ago, and they now are a source of erosion and water runoff. We want to see that these stands are have limited impact by invasive plants. Invasive plants can really hinder regeneration of trees, of herbaceous plants, and they cause a lot of lack of biodiversity. And this idea, as I already mentioned, is that stressors do not cause catastrophic impacts, right? That forest is able to bounce back and recover. And Liz mentioned this already, but old forests can have a lot of deadwood in various stages of decay. Deadwood is super important in our forests. It cycles nutrients back to the soil, makes it available for plants. It protects soils from erosion. So it's really good for actually keeping soils where they are, stopping storm runoff, right? So think about a log on a steep slope. As that water runs across the surface, it's actually physically going to stop that water and slow it down. They can also hold an incredible amount of water during times of drought, which is pretty good for ecological functioning. They can be a place for seedlings to germinate. Liz mentioned this. There are a number of our species that really need to germinate on dead logs: yellow birch, red spruce, eastern hemlock. They really like that substrate. And so sometimes we see a lack of regeneration of those species because there's not a lot of dead wood in our forest. And of course, they're a rich habitat for fungi, insects, all sorts of other life. And so this graph is showing, 3 sort of ages of forest maturing, partially cut old growth. You see a lot more dead wood, both standing dead and down in that old growth stand. And the numbers 1 through 6 are this score we use for decay class. So 1 being a very fresh log, 6 is basically soil. And it's along a continuum. We give them ratings based on how decayed they are. But we really want to see trees of multiple decay classes. That indicates that we have decomposition happening in different levels. We can also have in old forest lots of down trees and streams. And Liz talked about this. This is something I've been working a lot on, and I'm really excited about doing this more on private lands. But we do see in these old forests where natural processes happen, we just have really messy streams. And there was practices in the past to clean out streams, to even incentivize landowners from removing some of this material. We thought it inhibited some, travel, certainly in bigger rivers where we actually transported logs through. We had to remove these kind of impediments. We now realize they provide incredible ecosystem services, especially controlling storm flow, right? So we get heavy rainfall events. These sort of act as these natural log barriers, slow down. They reconnect the rivers and streams to their floodplains. So it allows the water to kind of flow over into that floodplain. They protect stream banks from erosion, create diverse stream conditions. So you get things like pools and waterfalls. And so we do know, and there's a number of fish biologists looking at this, that's really important for cold water fish like trout. And so we do see this in other work from Bill Keaton, colleague at UVM, showing that these, forests, depending on their age, and he uses these categories of mature, old, and old growth. And we see this, increasing amount of large dead wood in these streams. Old forests can also be better at intercepting and slowing down rainfall. And so this is when rainfall is coming down through the canopy. We see, depending on forest age, it actually slows down how quickly that rainfall gets to the ground. And this is, again, just because they're more complex. They often have really big branching structures. They have very complex bark that can actually trap water and slow it down. And so in this graph on the left, you'll see, the two different lines. You have a solid line, which is the rainfall amount, and then the dashed line is the throughfall. So that's how much water got down to the ground. And as you go to these older stands, you go to the 200-year-old stand, the space between those lines is bigger. So that's showing that less water, the same amount of rainfall, but it's taking longer for it to get down to the ground, slowing down that rainfall amount. And this is really important. This is an example on the right of that rain event we had July 30th. This was actually after the big, the big storm we had, but we're getting more heavier rainfall events, 7 inches of rain. And so this is really important to think how we can slow down water, how we can get it to absorb into the soil rather than having it run off and flood downstream areas. Old forests can support biodiversity. Again, Liz mentioned this. This is showing some examples of that. It's this complexity, especially things like dead trees with these cavities, like showing of the sugar maple on the left, and many that it can provide critical ecosystem services for us and for agriculture, right? So things like bats, birds, bees rely on these structures. These graphs show just that as you have more standing deadwood, more downwood, you get more bat habitat, which is bee habitat, in that can either live in these ground nesting situations or in these tree cavities. And it's really similar when we look at bats and birds across this spectrum. I just want to say that not every forest that we have that has some of the characteristics of an old forest has the same ecological functioning. And these are some examples. I travel all around the state and all around the region. I go to lots of different types of forests, and this beautiful old sugar maple. This is down in Danby, and the lore is that these trees were tapped before the Revolutionary War. They're very, very old. I've actually I use dendrochronology tree coring, and I've wanted to core them, but I don't have an instrument that's that big. I cannot get to the center of the tree. But one thing I see this is my intern Jill, her feet, those are invasive species. So that's barberry. The understory was really cleared of all species but sugar maple, right? People wanted to focus on the sugar maple. That's what made them money. But they cleared out all the other trees. It's very flat forest land in there. There are earthworms, so you see these other ecological impacts. Great big old trees, but it doesn't have some of these other characteristics like deadwood, like complexity, like regeneration that we would want to see in a well-functioning old growth forest. And another example from a similar type stand, this is actually not too far from us. And on the right photo, and you see this, the trees were really widely opened up, very park-like, and we get this understory of hay-scented fern, which is a natural fern, but it really inhibits regeneration of tree species. So there's basically no regeneration in this forest because of the hay-scented fern. We see that from some great work, including a local historical ecologist, Charlie Cogbill, who's a mentor of mine, has worked on reconstructing the pre-colonial species composition of our forests, so before European settlement. And we see that before European settlement, we had all the same species in our forests, but the composition in our forests has really changed because of how we've managed our land and the species we've cut or the species we've retained. And so we're seeing now in our modern forests, we have much more maple. People love maple. It's a really lovely species for many reasons. We see a lot of pine because that came in on those old fields. We see a lot of birch. We see decreases in species like spruce, beech, and chestnut, to name a few. So we really do have different forests now than we had back then. And of course, many of our forests face novel stressors that they've never experienced before. Invasive insects, diseases in plants. This left photo is showing an understory that's basically all invasive plants. That's honeysuckle. There's bittersweet in there that grows up trees. It's a vine. There's barberry in there. There's very few native tree species that can compete with those invasives. They're very good at growing and occupying space. The photos on the right, the top photo is near where I am on the Winooski. So that's showing a beautiful floodplain forest. All that green underneath is invasive goutweed. So there's no understory of native tree species that are regenerating. We also see this with beech trees. So the middle photo, beech is a beautiful native tree we have. Unfortunately, it's been affected by beech bark disease, which is a complex of an invasive insect, scale, and a fungi. And what it does when the trees die is they send out these root sprouts. So they're clones of the parent tree. And what they do is they create these dense understories of just beech. And those beech, because they're clones, will still get beech bark disease. And so they will never bite, they'll never really get big. They'll kind of go through this boom and bust period, and then they outcompete any other tree seedling to regenerate. So we see these monocultures of beech sprouts in many of our forests. And then the bottom photo is showing invasive hemlock woolly delgid that is killing our hemlock down in southern Vermont. We have the first evidence of mortality of hemlock woolly delgid. I work with the state of Vermont forest health team. They monitor these stands, and unfortunately, we've seen mortality. It's kind of incredible. This tiny insect can kill these trees. And as we've talked about, we have seen heavy browsing. This is an example. Sometimes we can't see evidence of browsing until you exclude browsing. And this is an example of county forester Matt Langlass, who established this browse sort of experiment. And so inside the fence, you see a lot of different species, and they're actually, becoming, they're not seedlings anymore. They're kind of pole-sized trees. Outside the fence where browsing still happens, there's no trees. It's mostly ferns. And actually, if you look closely, you do see some stems that have been browsed on. And so that's often how we see evidence of heavy browse, is we have to exclude the browse because it's been going on for so long, you often don't even see what's happening. And this is some research by looking across the northeastern forests at this, at the average number of saplings, and seeing, especially south of us, of seeing actually like not sufficient number of regeneration to replace the overstory if there was a disturbance. So we are at a point where we are very worried, a lot of us that are in the woods frequently, about the ability of our forests to continue because we don't have that younger age class in many of our stands. And so, this idea that our forests occupy a narrow band of conditions right now in Vermont and across the region, they're often novel ecosystems without a past analog, right? They look different than the forest did before European settlement. It will take centuries for many of these forests to develop into old growth forests with the complexity and ecosystem functioning that we would hope. And so, I do encourage and work with landowners and foresters who want to actively manage to use timber harvesting as a tool to accelerate the development of these characteristics. And that is really great for promoting resilience too. And it's resilience for that landowner, for thinking long-term about the benefits that they get from that forest, including economic benefits. It's resilience for our community and our state economically, right, to have a local source of resources, and promotes longevity of forests. And so some examples of this, so it's just showing examples of second growth forests, young forests, where folks are doing this kind of work. And this is in Williston at the Catamount Community Forest. It's really a lot of old field white pine. There's some big pine in there, but they're not very old. They're about 60, 80 years old. And so using timber harvest to create complexity by doing different things in different places, reducing competition around healthy trees to allow them to grow larger. So creating these canopy gaps, providing vertical structure in the forest. Girdling trees, it's a way to create standing dead trees. It doesn't exactly mimic what we'd have happen in nature, but it helps accelerate that process. We call those snags, standing dead trees. Designating permanent legacy trees to live out their full lifespan. And on this site, mark them with an L, for public outreach. But the idea is that tree would never be cut and is allowed to live however long it lives. It also then provides seed for that area behind it, which was opened up. And so we'll get some regeneration there. Leaving tops and limbs on site. Again, the benefits of dead wood are many. And so having sites be messy, getting folks to not clean up their forests. And I know this is a cultural thing. Folks want their forests to be tidy, but forests naturally are messy. And so leaving those things there. And there is a growing number of folks that are adding large wood back to streams. It's very cool. It's happening across a lot of parcels. Mostly the Nature Conservancy is doing this. Green Mountain National Forest, the state of Vermont is doing this. I'd like to see it happening more on private lands. And I will say that there is a lot of technical assistance. There's demonstration sites established throughout the state and the region. There's cost share available to landowners to do a lot of these work, including I've been working with, so this is a natural resource conservation services that provides cost share and technical assistance to landowners. I've been working with them to create a cost share for enhancing old growth characteristics in forests. And so that's really exciting. And there are a growing number of landowners, land managers, foresters that are employing these techniques around Vermont, which is very exciting. All right, so I guess I just have a summary slide. So a few
Wait to see what's on it.
few examples of growth forests in Vermont. There are forests that have or are developing characteristics of old forests. Old forests do provide many functions and services. I mentioned storing carbon, providing rich biodiversity, rainfall interception, controlling runoff. So many things that we depend on. But not every forest will develop the characteristics and ecological values of an old growth forest. So we can use management, and that does, there's a spectrum of management from passive to active that needs to be based on the conditions of the specific forest. There's no one size fits all management strategy for every forest. But we can use characteristics of old growth forests to help guide management to provide some of those benefits for resilience and services. So the challenge is, and will continue to be, working with landowners to identify the best management that aligns with the forest conditions and their goals. And so that's, something that I work very closely with landowners and foresters to really figure out where that lies. And that's all I got. Happy to take questions.
Thank you. That was great. Lots of information.
Yeah,
Pass
these around.
Very helpful to us. I'll kick it off. I guess I'm curious about, some of the forest examples you gave us of, particularly with the older trees intermixed with an understory of an invasive, and how is it that you work with that landowner, and what's been successful in kind of liberating that forest and also suppressing those invasives?
Yeah, so I don't directly work with the manager. I provide guidance for landowners and foresters. So it's really a consulting forester or county forester that would help an individual landowner. But really, the guidance I give for folks with invasive plants is to try to limit spread. There are places, Champlain Valley is one of them. They're the islands up in Lake Champlain, where pretty much the entire understory of a forest is invasive plants. It's really daunting for a landowner to think about, how do I deal with this? And so I say chip away from the outside in, right? So kind of try to limit that population from spreading to new parts of your forest. If you can kind of tackle it outside, instead of lots of people go to the center of the invasive plant infestation and try to get it. I do hear from a lot of foresters, and I've had personal experience. I've done invasive plant removal for many years out in the Pacific Northwest, is that herbicides are really, if well used and really thoughtfully used and really intentionally used, are really effective. It's to mechanically remove lots of invasive. It can be really labor intensive. You have to go back year after year. For small populations, totally doable. You can hand pull things, and that's fine, individual plants. But for large populations of plants, it's really helpful to, so people use what's called the buckthorn blaster. It's a little spray bottle with herbicide in it. You cut the stem and you apply it exactly to the cut area, so you're not broadcasting it. And that seems really effective. And I hear that a lot from both landowners and practitioners.
I guess maybe the answer is, I was thinking that some of the management for old forest characteristics might be helping address that monoculture in the understory. Does it?
Yeah, you really do have to treat those invasive plants because they're really good at what they do. They're invasive for a reason. And so usually they'll keep existing there. So that usually has to be addressed, is those invasive plants, if they exist in their forest. You're not going to get a lot of regeneration with those plants there, especially large populations of them. Yeah, unfortunately. Yeah.
So my other question is that we hear about accelerating the characteristics of old growth forests through management, which I understand. But if it's for, a long-term landowner goal is management, that seems like a more sustainable way of managing the forest. But at what point, you mentioned there's a legacy tree identified, but it seems like if you're continuing to harvest, you're never really going to get to an old forest.
Yeah, so it depends. It depends on a landowner's parcel size, right? So if you have 30 acres, there is a different amount of timber harvest you can do if you have 200 acres. But yeah, the idea behind legacy trees is to designate them to never be cut. And so that's a strategy to prevent, if you are going in a forest and you're managing it every 20, 30 years, you will not potentially ever get old trees. And so leaving either individual trees or patches of trees to live out their full lifespan allows for that to happen. But it does take long-term planning. And so through the current use program, landowners are required to have a 10-year management plan. I do encourage even folks that aren't in the current use program to have a management plan because it helps people think 10, 20, 30 years in advance, which is really critical for managing forests. You can't just think about next year. A lot of these processes happen slowly and develop over time, and there's unexpected disturbances that you might encounter. Yeah, I mean, it's really comes down to landowners' goals if they want to include some of these. I encourage it, even if they don't want to promote old forest characteristics, having legacy trees that live out their full lifespan provide a source of seed. They're trees that are well adapted to the site. They'll be future source of deadwood to that forest. So they provide a lot of other benefits that can confer resilience to that stand. And so a lot of these practices can work for folks that want to accelerate old forest development or just want to have a well-functioning and resilient forest. And so we can kind of take some of those characteristics and apply them.
Other questions? Representative Austin and then Labor.
Is there any thought, I know you thought of this before, but of planting trees in a forest that will, at some point, become like very old growth?
Yeah, so so there are folks that are we've always planted trees here in Vermont. It's happened. We have plantations, especially when we were not like early 1900s when we were down very low forest cover. We had the Civilian Conservation Corps. We planted many, many thousands, millions of trees throughout the region and the state. And then there's a new movement going on right now with climate change is to plant what we call future climate adapted species. So this is this idea that the climate is changing really quickly. There's species we know that will be better adapted to future climate, warmer, dry, somewhat drier conditions, heat waves, things like that. And so folks are thinking about adding those as components. It is possible to do. Our biggest hurdle right now is it's hard for landowners or foresters to find those trees. We just don't have great nursery capacity. We don't have a state-run nursery in Vermont anymore. We do have access to the New Hampshire nursery, but they might not have every species that we would want to plant here in Vermont. So it is limiting where we get source of that stock. There are some new outfits that are doing it, some consulting businesses that are starting small nurseries to do planting on private landowners' land. It can be expensive, it's labor intensive, and unfortunately, all the trees don't survive. And you need to protect them from deer is kind of the big critical part. So, because as soon as you plant that out in the woods, that's, candy for the deer. And so it is, generally natural regeneration is going to be the best and cheapest, but there are places where it makes sense to do that, to restore some species, to have future climate adapted species. We do have a big bottleneck with labor force, people to do the work and stock to plant.
Thank you.
Representative Labor.
Thank you. What I'm finding in my forest, and I've got almost 200 acres, is that the emerald ash borer doing extensive damage to the older trees because they are the taller.
Yeah.
The other thing I'm noticing is that because of climate change, it's hotter, drier, and gives a longer growing period. So the trees are, their canopy is growing out and it's growing up, creating a sterile odor underneath the floor. So there's a lot of fern growth. And then I'm getting wind damage when a burst comes through. And anything over 60 to 70 feet, it's hammered. And that's an economic loss because I've been in use value since 95. And I'm on my third run of forestry plan development right now. And I'm having to readjust the floor management
Mhm.
based on weather.
Absolutely.
And that's concerning.
Yeah.
I've participated in 2 USDA NRCS EQIP grants
Great.
to take care of a portion of the woods that cut in the early 70s with a heavy cut.
Mhm.
And there was nothing for the deer or the animals to eat.
Mhm.
Well, they're back. But the cost sharing, you got to love the land. You're not going to get your cost back. But,
Yeah, not gonna fully pay.
it's nice to see. And I think my next goal will be to develop a succession plan for the woods.
Yeah.
My children are nowhere around.
In Vermont Woodlands Association, I don't know if you've seen that they are doing succession planning with landowners. It is a big,
Email.
yeah, it is a big, but I just want to say, like, we benefit and rely on in our state as private landowners that care about their woods, right? I mean, I love living and working here in Vermont because most everyone loves or cares about trees and woods, even if they don't own forests, they recreate in forests or, and that's great. But we do, most of our land is privately owned and we rely on people really caring about, and often it isn't, I hear this from landowners a lot, the increasing economic costs. Heavy rainstorm events we had last 2 years caused incredible damage to roads, to culverts, cause culverts are not cheap, and then, windstorms. I've heard stories about, sugar bushes, a lot of trees and sugar bushes coming down in windstorms. That's an economic cost. So it is really, it's a growing concern. I'm hearing people really want to do the right thing and are getting challenged by how to pay for it and get it done. Yeah.
Well, there's nothing attractive about a 7-foot-high roof wall.
Yeah.
That's small. Are you kidding? I got.
One more question from Richard, Representative Pritchard.
So this may be unrelated to any of this, but something that I've noticed over the last couple of years in my area is, I don't know if it's moss or lichen, but I'm seeing it on everything. I'm seeing it on fruit trees. I'm seeing it on anything, covering the whole tree.
Yeah.
Our dog fence, which has wood on it, is covered. What is that? What is it?
Well, I don't know specifically. Okay, well, in general, and I'm happy to come back in and I do also like a climate impacts talk and talk about how our climate is changing. And one of the things that we're seeing more rain, right? Our rainfall in Vermont has increased about 20%. It's just more humid, right? And so what we have, when we have warmer air, it can hold more water. So that means that air is more humid. And so we get conditions where those humid conditions, we had this, not this summer, but the prior summer, I don't remember, but it was just so wet the entire summer and all the leaves of the trees developed fungi on the surface. And so a lot of them looked kind of brown. That is, we saw this on like apple trees. I mean, I heard from all sorts of folks. It made the fall foliage season pretty crummy.
It's very
yeah.
noticeable.
And so that's the thing. And we get other foliage diseases. White pine is a species that now has, it's all native fungi. But when we have really warm, wet springs, that fungi just proliferates and it causes early leaf drop of the white pines. And so they look really, turn brown, they lose their needles. And so from a health perspective, none of that's good for a tree, right? 1 year is okay. A tree can, deal with it. We see this repeatedly of time, year after
And
year.
it doesn't discriminate.
No,
It's
yeah,
on every-
yeah. I
every-
mean, yeah. And, I think, I haven't seen a lot of research, but I think anecdotally, again, I'm in the woods a lot. I see a lot of mushrooms.
Mhm.
Again, right? Mushrooms like humid, wet conditions or fungi. I think that we're seeing that, right? So like just everything's wetter, more saturated for longer periods of time. That said, we also are likely to see some drought conditions. And that seems weird when we have more precipitation. But again, that hotter air we see in the summer, especially July, August, we could see drought. We did see a lot of fires this year in Vermont. It wasn't, anything out of the long-term, record, but fires are just so uncommon here. It's hard for us to really see a trend, but, Maine, New Jersey had increasing amount of fires. And so it's this weird thing where we do have these wetter conditions in some years and at some parts of the season, and then we also can have drier, hotter conditions. And so it's just really like what we call is like weather whiplash is a term we use, where we're going from like one thing to another, right? We have snow, then we have melting, then we have drought, then we have, and it's just really a lot of variability in our weather conditions that's driven by, they're not all caused by climate change, but that variability and that trajectory is driven by changes in our climate.
So thank you. That was
Thank you.
really edifying. We will, we may take you up on the offer of the climate change talk.
Absolutely.
Members, we'll take a 5-minute break and then we have